Hello and welcome to our next part of the MotorDoc podcast. We're going to talk today, and we're going to finish up, I should say, a quick discussion related to the compressed air systems before we move on to some other things. So be ready. In any case, we're going to start with this example here of a compressed air system. We've noticed this happening a lot lately, especially in the package systems. It's not a particular brand, it's a number of them, and they're doing a number of different strategies, but we'll cover that here in a second. So let's go ahead and take a look. Let's see if I can get over to the next image. Here we go. This is the nameplate for this particular machine. Now, they've had a lot of problems with this machine. It's failed a number of times. Everybody's been pointing fingers, and the OEM had done the setup for the compressor. But I want you to notice something here. So 440 volt, when 440 volts is supplied, it's got a service factor current rating of 810 amps. At 460, at 60 hertz, 780 amps. Now, this is an across-the-line machine. The other thing we'll note is that the service factor adjusts down if the temperature gets above 40 degrees C. Now, 40 degrees C is 104 degrees Fahrenheit. So if they get up towards this 55 degrees C, which is very possible in an enclosed system if cooling is not working properly, this could drop it down to the actual just straight full load amps. But in either case, we're going to say we're shooting for at 460 volts, somewhere about 780. But you can notice in a 20 volt range, it changes by about 30 amps, so it decreases over time. So the particular machine we're going to look at, we're going to say it drops to 470 volts, or up to 470 volts. That would mean that this current, if we assume it's linear, it's really not. As you begin to saturate, as you increase voltage and everything else, it's more of a logarithmic curve. But in any case, so 470 volts, we'll say then that will be half of that difference, which is about 30, so 15. So technically, it would be at, say, 765. So again, a lower current than this. RPM here 1788 and 1789. As you increase the voltage, you notice that the RPM goes up. So that's also important because it means that it's something you should consider in any case with an electric machine. If you're not running at nameplate voltage, say you're running higher than nameplate voltage, which is very, very often, your RPM will go up, meaning that you can't really use that as a methodology for determining load. It takes a little bit of calculating. So when we take a look at this machine, we're going to notice that as well. So let's go ahead and take a look at the machine in question. With the electrical signature analysis. So here we are, not too bad. Let's take a look at the data. Yeah, there's casting voids in there, which adds to some of the concerns. Give this a chance to start up. Again, as I've mentioned in past presentations, well, you can't see across the bottom, but I have a lot of stuff running in the background to do this. Ignore the power factor. That is a function of the way we set it up. We're not going to worry about this data here. We're going to worry about our running current and our voltage. You notice the voltage is about 467, so we'll say 10 amps different, right? So we're going to say that. But you'll notice here, we had said the maximum current is supposed to be, in the service factor, about 780. We are way, way up there. We are on average. You can notice there's also a current unbalance here. There's another defect in the machine. But 854 amps at an average of 467 volts. So in effect, the motor is most definitely overloaded. Not quite to 206%. It's going to be more like 160 to 170% load. So we'll get out of there. And just losses associated with some of the other stuff behind there, unbalanced losses and the like. There's a little bit of unbalance there. But in any case, so that is one of the primary concerns. And we're running into this a fair amount. We'll see it in bad bearings. This one here in particular, both bearings across the very short time it's been running are now showing indications of failure. Let's get out of this. And we will move on to a slightly different discussion. So let's go ahead and pull this up here. So part of the thing that can cause this these overloads, in addition to improper settings of the compressors, and unfortunately some of the comments we've had from some of the technicians associated with the compressors is, well, they set them to these points because they feel the equipment can handle it. I'm sorry, motors are designed to run to a maximum. The ones we have seen coming out have obvious overload conditions. I mean, everything from, at another plant we were seeing something similar, 160 to 210% load. That means all the safeties were set aside. It was so bad that the end user had to bypass their circuit breakers in order to get the compressors to run to the points where they were supposed to run in order to keep production running, instead of setting it, but also instead of looking through and identifying compressed air related issues. That can be everything from, compressed air, the pressure, to evaluating leaks. I mean, leaks, basically, a leak survey or using leak surveys in a planned maintenance program can usually pay for itself immediately. I'm talking about, paybacks, if you're going to do a simple payback, in as little as a day. So let's go ahead and take a look at some of that real quick and some of the tools that are available to make our lives easier. This one here, this is out of the Department of Energy's compressed air manual. This is the section on air leaks. We're gonna come to here first. So these air leaks can be through all kinds of things. They can be point of use. They can be just standard nozzles. It can be holes in the system, failed gaskets, problems with condensate systems, pressure drops across regulators. All kinds of things can cause it. But anyways, let's take a look at the leaks. And then I'll show you a quick leak table that you can obtain right from the DOE as well. And these links are going to be in the description. So this one here, this is on page 28 of this manual. It basically says we'll take a small, like a 1/16 of an inch. Flow rate is 6.5 cubic feet per minute. And the cost per year comes out to be about $1,046, assuming 10 cents per kilowatt hour and round the clock. Okay, so most of the tables are based upon 8760 hours, which is 24/7. So how can we figure out what our potential is? Well, the standard, if I go by the AEE standards or even the Department of Energy standards, as you can see, recommends that you stay in the 5 to 10% range or less as far as leakage. Now, why? Well, it's because if you tried to hunt down every single leak, you'd go insane. But in any case, so to figure out what the leakage looks like, there's a couple of ways of doing it. This one here is a system where you have all of your equipment turned off, all of the loads basically for the compressed air system. You do this during an outage, or if you're only working 5 days a week on the weekend, something along those lines. You run it, you see how long it takes to cycle, so on-time load, off-time load, things like that. And then they have a little calculation for figuring out what that is. Another way of doing it is by using MEASUR. As you remember, we talked about this a couple of times. This has all the calculators built in right under compressed air. So as you can see, here's one here, compressed air reduction. That means pressure reduction. Air pressure reduction is here. Compressed air reduction means removing air usage things. Here's an air leak survey. Bleed test. This is the one we're going to talk about. This one, I remember the early days we talked about this. It's literally figuring out the volume of a garbage bag and putting it over the leak and counting the seconds it takes to fill that garbage bag, and then knowing the volume of the garbage bag, which is part of it, part of the calculation here. You then can figure out your square feet per minute, or cubic feet per minute. I'm sorry. So let's take a look at the compressed air leak the bleed test. This is the other one. So in a bleed test, what you do, let's go ahead and we'll just hit generate a sample. Okay, on a bleed test, you have to figure out the volume of the compressed air system. Now there's, in the manual, in that other manual, there is a methodology for figuring that out relatively quickly. Certified energy managers will also have calculations for doing that. That's the one through AEE. But in any case, you figure out the total volume. That means that's how much compressed air is in the piping, the receivers, any storage tanks, any other storage tanks, anything, and you have it there. You put in the normal operating pressure, and then you figure out what the lower pressure is. So how long are you going to time it till it hits that? And then the time will be in minutes. So in this case, let's say we have a total volume of 100 cubic feet. Normal operating pressure, 150 psi. Let's do something a little more realistic. Let's say 110 psi. Test pressure, we'll let it drop down to, let's figure out a reasonable time and say we're going to allow it to drop down to 90 psi. So that's a small drop. That means that's going to keep your time a little bit better. And let's say it drops down to that in about 10 minutes. Well, then here we go. We have 17.01 cubic feet per minute. Now, at about 18 kilowatts per 100 cubic feet per minute, you can then use that to come out with a quick calculation. So that's one thing. Now, there's all kinds of other compressed air tools that are available to us for, other things like leak survey. This is where you can total up the number of leaks, come up with the actual dollar calculations. This is a way to calculate out to SCFM, which is standard cubic feet per minute. This is basically SCFM is what we use in a lot of the calculations. And then there's a lot of other things for sizing and everything else. And then, down here comes up with, I believe this also gives us our cubic feet. Yeah, so we come up with pipe size and everything else. It's going to give us our total volume and then any type of leak rate. So in any case, that is those are some of the tools. I highly recommend you go and play with it. There are videos on YouTube that go through how to use this tool as well. So let's go back, and I promised the other one. Now, if I'm going through, I've seen some conversions for ultrasound to air leak. Generally, those tend to be nice and conservative. I mean, I like ultrasound for air leak detection. I think it's a great tool for that. And then they now have some of the ones that will actually map out. So you'll have a device, and on the back you'll have just a bunch of ultrasound receivers and a screen on the other end, and you just point around, and it does kind of like infrared, where you'll get a color chart, and it'll show severity, or basically help you pinpoint exactly where the noise is located. Probably a tool I'm planning on investing in here shortly. So Yeah, so here we go there. Let's go ahead and take a look at that chart. Now I'm going to have this one in there as well. You can see this is another Department of Energy chart. This is the chart we use when calculating losses in general. So here you see the orifice diameter or the size of the leak. Sometimes you have to estimate, but if you can actually see it, you would then be able to say, okay, I have an 1/8 inch leak. So, you know, pretty good size. At 100 psi system, that's 25.2, right? That would be 25.2 SCFM. So that I can then use for, CFM, 25.2 CFM, and then I can use that for my calculations. And here are the calculations here. So cost savings, number of leaks, times the leakage rate, times, which is off that chart, times kilowatts per CFM, which they show as 18 kilowatts per 100 CFM, times the number of hours of operation, times the cost per kilowatt hour. Tend to use that. You normalize it. You throw in your demand. Now, the way demand works, and we'll talk about this at another time, depends on your rates and everything else, and that's a difficult one to use sometimes. But in any case, you'll come up with this, and that means that if I come in and say I have a 1/16 of an inch leak and 5 cents per kilowatt hour, as you could tell, this is old. So we'll take that 1/16 inch leak. That's 50 leaks times 5.72, which is the CFM calculation, times 0.61 times 0.18 times 7,000 hours times 0.05 is 10,991. Now it's really easy to say, okay, if this is 10 cents, then that doubles to basically 22,000. So in any case, you can do that across all of this in order to get an idea of what's going on in the plant overall. And you can usually, as I mentioned, justify the leak survey, including repairs, just by identifying and repairing those systems. And that doesn't even include the reliability and maintenance improvements in the facility, because you're going to have less loading and unloading, less loading basically of the compressor. You're going to have less wear and tear on the system. The leaks aren't going to get larger. Plus, you're going to get cleaner and drier air to the point of use. I believe that is pretty much my plan for today. We've been a little busy, so I'm keeping this one relatively short, but I did promise a following one on compressed air systems. We will next week probably do something a little different. I think we'll be at a point where we can discuss some of our initial findings in the comparison of the kilowatt off of an ESA device to vibration data. We had some bumps going on, and we had to make some adjustments to software, but then we have been able to successfully get everything in line. So the nice thing about the tool that we're using is we're going to be able to line up exactly kilowatts to vibration and ESA data to vibration data. So we can start showing you how vibration and ESA look very, very similar. With that, have a great day. Have a great week. We're going to be doing training at a motor repair shop this week with some customers with the electrical signature analysis devices. That'll be fun. I'll do some follow-up and probably show some data as we discuss our findings next week. With that, have a great day.